Welcome to Lecture 23. So today, just as we talked about practical issues that you run into with spiral pulses, such as the rotations that you get when you have a delay and when you have off resonance, we're going to discuss the same kinds of issues for echoplanar and spectral spatial pulses. So specifically what we're going to talk about is the effects of B0 and homogeneity. We're going to talk about delays between the RF and gradients, right? That is, delays between the start of the RF and the start of the gradients during the waveforms, during the playout of the pulse. And we're going to also talk about the effects of eddy currents on these two types of pulses. So first we're going to talk about B0 and homogeneity, and specifically their effect on EPI pulses. So why do we care about B0 and homogeneity? Well, we care about it because B0 inhomogeneities create frequency inhomogeneities, right? They create frequency inhomogeneities. Since we have that the frequency inhomogeneities as a function of space are equal to gamma times delta B0 of x, right? So where gamma here is the gyromagnetic ratio, right? So this equation relates a change in frequency at a given location x to a variation in the strength of the main magnetic field at that location. Okay, and so for EPI pulses, this manifests primarily as a spatial shift in one direction, primarily. It primarily manifests in the blipped direction, or the phase-encoded direction. So here's a graphical illustration of that. So if we say that the RF pulse starts playing out down at minus ky max down here at the beginning of time, then as it plays out RF here and then moves up here and then up here, then up here, then up here, time is evolving, right? All that time. And so then a phase evolution, a phase accrual is occurring due to that off resonance, right? So here's the off resonance delta F. So at the beginning of time, at the beginning of the pulse, we have a zero phase shift due to off resonance that then builds up to the end of the pulse when we get this large off resonance shift. And so then the maximum of that phase shift will be 2 pi times t, where t, capital T here is the duration of the overall pulse, times the frequency inhomogeneity. And so in the image domain, what that's going to do is shift our pattern vertically along the y dimension, right? So then the ky dimension is this way, so then the y dimension is this way, and the y dimension is this way in the image domain. So a phase ramp in Fourier space creates a linear phase ramp applied in Fourier space results in a spatial shift in the image domain, as we've seen before. Okay, so for example, an echoplanar pulse with a duration of 10 milliseconds, a frequency shift of 100 hertz will give us a phase roll of 0.01 times 100, right? So the 0.01 is 10 milliseconds, and times 100 hertz. That will give us one phase cycle, meaning that the phase will go from minus pi to pi, or 0 to 2 pi, across excitation k-space in the ky direction. Right? So effectively, we've applied this phase roll to our excitation pattern in k-space. So then the excitation pattern in the image domain, the mxy pattern, will be shifted by one resolution unit in this case, or that will be equivalent to the resolution of the trajectory, which is delta y, which is equal to 2 times ky max, right? So that's how much it will shift due to this one phase cycle across k-space. Okay, so that effect isn't particularly complicated, but it's even more intuitive. The effect of off resonance is even more intuitive for spectral spatial pulses. So if you recall that a spectral spatial pulse is like an echoplanar pulse with the blipped direction mapped to frequency, right? So we can expect that B0 inhomogeneities, that is frequency shifts, will shift the excited pattern in the spectral dimension. Primarily. There will also be a shift in the slice direction, but primarily you'll get a shift in the spectral dimension, right? Just because that's the one that's encoded more slowly. Okay, so water can end up falling out of the passband, while fat can come into the passband. So that is, we end up with a fat selective pulse. That's what can happen with off resonance, right? And so here's a graphical illustration of this. So this is a spectral profile of a fat suppressing or a water selective spectral spatial pulse. So we have a nice high profile. This would be the MXY axis. We have a nice high profile on water, and so if there's no off resonance, then water is at 0 hertz and it sits right in the middle of that profile and is nicely excited, while the fat sits right in the trough, in the stop band, right? But if we have about a -2 ppm shift, then we're going to get that fat is going to shift almost about halfway, or more than halfway actually, back towards the on-resonance water signal, and so that means it's going to start to shift into the passband. It's going to start to shift into the water band, whereas water is going to fall out of the passband, so it's going to fall into the stop band, and thus this pulse will end up being a fat selective pulse. And so this is really a catastrophic failure for the pulse. Okay, what about delays, right? Delays between the RF and gradients. Well, these have different effects on the two main echoplanar trajectory types. It's going to have a different effect on blipped pulses or bipolar pulses than it's going to have on flyback pulses. And to see this graphically, I've plotted RF envelopes as a function of k-space for the two cases, and shown what happens when there's a delay, right? So this is the beginning of time, and this is the end of time for the pulse. And so if the gradient starts a little bit earlier than the RF, then you're going to start moving along in k-space before the RF starts, right? So then the RF pulse is going to be shifted this direction. It's going to be shifted a little bit this way, right? This first one is going to be shifted a little bit this way, and then it's going to fall into the blip up, and the next pulse is going to be shifted the opposite direction, and then then the other one the other way, and then the next one the next way, and so on and so forth. So every other pulse is shifted the same way, but adjacent pulses are shifted opposite directions in kx. Now, on the other hand, if you have a delay in a flyback trajectory, then all of the pulses are shifted the same amount in the same direction. Right? So these are the results then are going to be very different for blipped or bipolar pulses than they will be for flyback pulses. So as we've seen, and have seen many times before, a shift in the excitation k-space domain is equivalent to the application of a phase ramp in the image domain, right? So before we saw that field inhomogeneities will put a phase ramp across the k-space domain, and so then we get a shift in the image domain. Now we have the converse situation where we have a shift in the k-space domain, and we'll now get a phase ramp in the image domain. Okay, so here's an illustration of what happens. This is a pulse that is not shifted at all, right? And so then this is the subpulse profile that you get, and it will not have any phase ramp across it due to any delay. But what happens if we shift it a little bit this direction? Well, then now it's delayed a little bit that way, and what we end up with is a negative linear phase ramp across the slice profile, right? So we still have zero phase in the middle, but we've got a linear phase ramp as we move away from z equals 0. And we get the opposite phase ramp if we shift the pulse the other way, right? So what you can imagine then, what I'm going to say next is that then adjacent lines in k-space are going to excite slice profiles with opposite phase slopes, right? And so this is going to be a problem. And in particular, this is really a problem for blipped or bipolar trajectories. And so what happens is that every other line, as I said before, gets a different phase slope, right? So what we can think about, let's consider an echoplanar pulse, right? So a blipped echoplanar pulse. So it's going to go, its trajectory is going to start here, then go up here, then there, and there, and so on and so forth. Now what we can think of this because everything is linear here. We can just do a thought experiment here and separate this pulse into two pulses, right? Two pulses with half the field of view, wherein each line of these two pulses runs in the same direction in kz. So actually, this is illustrated for a spectral spatial pulse. We can also think of this as for a echoplanar pulse. But in any case, you can think of this as two interleaved echoplanar trajectories, one represented by the orange lines and the other represented by the green lines. And so for each one of these, the delays are in the same direction, right? So then the phase ramps are going to be in the same direction. Okay, so normally what we design the pulse to do is implicitly what we design the pulse to do is for the side lobes from these field of view over two trajectories to cancel out, right? So they must have a pi phase shift between them, right? So then without any sort of delay, there's naturally a pi phase shift. So then the green curve would be like that, and then the orange curve would be flat like that, and there would be a pi phase shift that would be constant throughout the slice profile. And so then the field of view over two side lobe would cancel out, right? Now remember, this is the field of view. This field of view over two side lobe is the one that's sitting on fat, right, in the stop band. Okay, so now what happens though is when these adjacent lines have opposite phase shifts, they're now going to have opposite phase slopes applied to them, right? So then what happens is that, yes, still in the center of the slice profile, you are going to get nice cancellation because there's no additional phase shift there. But away from the center, you're going to get phase shifts in opposite directions, and so you're going to start to get more coherent excitation again. And that's a significant problem, and that actually manifests in a enhancement of these side lobes. Okay, so because the phase ramps have opposite slopes for excitation patterns generated by the positive versus negative going k-space lines, right? So the positive going ones here are the orange ones, the negative going ones here are the green ones. So because those two sets of k-space lines have opposite slopes, or excite patterns with opposite phase slopes, the field of view over two side lobes from those interleaved sets of lines fail to cancel out for z for non-zero z, and what we get are field of view over two ghosts. Okay, and so this is actually, I'm showing here an experimental echoplanar excitation pattern that I actually acquired myself a few years ago. So here's the square that I actually wanted to excite in XY, and here are these two side lobes that are generated, and you can see that, so nominally the pattern would just contain this square, right, and these guys would be 0. But when we have a delay between the RF and the trajectory, we get these two side lobes that pop up that look a lot like the opposed null side lobes that we get from a spectral spatial pulse. But this was actually an echoplanar pulse. And so now we get these n over 2 ghosts, but you can see that they are still 0 in the center of the pattern, just as we would expect, because in the center of the pattern the two side lobes are still out of phase. But then as we move away from Z, they come into phase and we start to see these amplified n over 2 ghosts. And so here's a schematic representation of that as well. So here's the targeted pattern and these n over 2 ghosts that appear when we have a delay in the trajectory between the RF and the gradients. Okay, so note that I have been focusing on all the deleterious effects of delays on bipolar pulses, and that's because for flyback and EPI pulses, or for flyback EPI or for flyback spectral spatial pulses, there's really no significant effect. Delays have really no significant effect. They're immune to these delays because all of the subpulses are shifted the same direction, so all that we get is a little bit extra linear phase ramp across our excited slice, but the slice pattern itself is not distorted at all. Now for bipolar EPI pulses, what we end up getting are field of view over 2 ghosts, just as I showed on the previous slide. For opposed null spectral spatial pulses, we just get essentially the same thing. It's analogous to the blipped EPI. We get bigger opposed null lobes, which will increase the fat signal. And for a true null spectral spatial pulse, though, we also get no effect, just as in the flyback pulse. Now, in that case, the side lobe, that's because we have placed fat at field of view over 4, right? So this delay causes an enhancement of the field of view over 2 side lobe, but in a true null spectral spatial pulse we didn't place fat there. We put it at field of view over 4, and so we get no effect then from this. Okay, so the last thing we'll talk about here are eddy currents. So what are eddy currents? These are electric currents that are induced in conducting structures in the bore of the MR scanner by time-varying magnetic fields. Right? So what happens is that we have these coils, right? These coils that that create the gradient fields, right? So inside the scanner we place these coils, and they are going to have currents running through them, right? And we design them to create a certain magnetic field, right? And most of that field is going to point along the z direction. Some of it will not, obviously, but it will mostly point along the z direction. And then we switch these currents, right? Because gradient fields are time varying. We switch these currents running through the coils on and off, and change their amplitude continuously. And so whenever we're changing those currents, we're going to be inducing currents on other conducting structures inside the bore. So for example, if we have this current running through this coil, it's going to create some magnetic field B, and then it's going to induce some other current, I sub c here of T, on any other conducting structure. For example, the bore tube in the scanner. Also, we induce currents on the metal of the RF coils themselves, anywhere that there's metal, right, conducting metal. Okay, so eddy currents, though, in turn produce fields that oppose the gradient fields. Okay, so this coil creates this field B here, but then this current that it induces in this conducting sheet is going to run the opposite direction, and then it creates a B field that opposes this B, right? So each time the each time the gradient changes amplitude, the eddy currents are going to be induced in those conducting structures that then will decay over time as the gradient field stops switching. So since there are many conducting structures in the bore of different sizes and orientations with respect to the gradient coils, we get lots of different time constants. So usually we model these guys as decaying exponentials. We model these currents as decaying exponentials with potentially many time constants. So we're going to model these as a sum of terms of increasing spatial order. That is a Taylor series expansion as, so here's the eddy current field that is produced at a given position x and t, and this is a z-directed field, right? I'll point out that's a field that points along the z direction, or along the main field direction. So that's going to be a B0 term that is not spatially dependent, right? So that's going to be like a global frequency shift. And then there's this a linear term, right? So let's see, so this is a global. Then we have a linear term, right? So this is a linear function of space. And then we also are going to have higher order terms. Okay? Okay, so a bit more about these three terms. So the B0 of t term, again, is spatially uniform. It is equivalent to a time-dependent frequency shift. And you can correct it by frequency tracking. That is, changing the frequency of the transmitted RF pulse ever so slightly as to remain unresonant in spite of this B0 shift. And so the vendors have actually got this implemented for basic trapezoid pulses that are the most commonly used gradient waveforms. They actually have a model for the B0 term that will be generated by an input trapezoid, and then that spits out the predicted B0, and then they modulate the pulse modulate the RF waveform up for that. Okay, so in the linear term, G of t behaves just like another additive gradient. additive gradient. Okay? And you can correct it by gradient preemphasis, right? Since we can control the gradients we input, if we can measure this g of t, this additional eddy current g of t, then we can correct it pretty easily by gradient preemphasis. And essentially what that is you just add minus g of t to the input waveforms. Sorry, to the input gradient waveforms. Okay? And then the higher order terms, these guys are harder to correct, right? Because we don't have any gradient channels, in most scanners at least, that are capable of just playing out arbitrary higher order field gradients as a function of time. They are, however, the motivation for shielded gradients. So basically these are gradients that have a lot of a big metal sheet around them to prevent currents from being induced on other metal structures in the scanner. And they are usually ignored because we just don't have anything that we can do about them in a sequence. Okay, so as you can read in Bernstein, the time domain model for the linear eddy currents is equivalent to a set of inductively coupled LR circuits. That is, we have an LR circuit model for our for the gradient coils we actually put in the scanner, and then we can also create LR circuit models for the eddy currents, the structures that induce that carry the eddy currents. And these circuits are coupled via essentially transformers, the two inductors coupling magnetic fields to each other. So basically what we do is we say that the gradient is equal to the eddy current gradient is equal to the time derivative minus the time derivative of the gradient waveform we actually intend to play out. So it's minus this because it opposes that waveform, right? And then that is convolved with a multi-exponential model E of t. So the multi-exponential model then comprises a Heaviside step function, right? That's a function that is just 0 up until time 0, right? So it's 0, 1, and this is t, right? So this guy is just a Heaviside step function times a sum over time constants, right? A sum over decaying exponentials. So then we have the sum over n equals 1 to n of these coefficients alpha sub n times exponent of minus t over tau n. So the tau sub n's, the alpha sub n's are the coefficients of the decaying exponentials, and the tau sub n's are the time constants, right? So this is a decaying multi-exponential model for the eddy currents. And what we do typically is we fit this. There are various fitting procedures that the vendors and others have developed in order to determine these coefficients for a given scanner setup. The problem is that these guys will change a little bit as you change the metal environment of the scanner. So if you change the RF coil, they're going to change a little bit, which we do all the time, for example. They're also not necessarily accurate for all that particularly accurate for gradient waveforms that are not trapezoids, right? So, for example, for spirals, the gradient amplifiers can behave a bit non-linearly, and so we don't necessarily get this same model out if we were to apply it to spirals. Okay, so here's an example, though, of what happens here and how we can compensate it. So here's a gradient trapezoid that we might apply, right? That's capital G of t there. Its derivatives are these square functions, right? So it's only changing during the ramp up and during the ramp down, and the rest of the time it's not changing, of course. So then G of t, right, the gradient is going to be this guy convolved with this exponential model, right? It's going to be these rect functions convolved with the exponential model. And so it's going to be sort of this slow rise up and then decay, right, on each side. And so then the total gradient is going to be that eddy current field, G of t, plus the original one, capital G of t. And so then these are the two superimposed on each other. Then we have G of t is still nice and sharp here. But then the actual gradient that we get out is these two added together. And so you can see that the negative part of the eddy current gradient is going to detract from the from the plateau a fair bit, and it's going to make it seem like it's actually starting a little bit later in time, right? So that's one of the sources of these delays we keep talking about. And then on the other end, it's going to actually not decay away as quickly, right? So what are the effects then on echoplanar and spectral spatial pulses of eddy currents? Well, the linear eddy current terms, the G of T's, are going to cause effectively just mostly delays, right? So the gradient effectively occurs later, so we get a delay. And we saw already what happens to different spectral spatial pulses and echoplanar pulses when we have delays. B0 eddy currents, on the other hand, are going to be a frequency shift, right? In fact, they're a frequency shift that is proportional, it's a proportional symbol, to the gradient. And so for flyback EPI or flyback spectral spatial pulses, what this will do is give us a small spatial shift in the slice direction. Because now everything is just a little bit off resonance, so the slice is going to move a little bit. So that's no big deal, though. It's going to move a pretty negligible amount in practice. But for a bipolar EPI or opposed null pulse, we're going to get oscillation in the KY or KF directions. So this is going to be oscillation. It is oscillation in KY for an EPI, or KF for the opposed null pulses. And this is going to cause a field of view over 2 side lobe, right? Because it's going to be a sort of a 1 minus 1 oscillation of the RF pulse along this direction. And so it's going to give us a field of view over 2 side lobe. And it's really actually a catastrophic failure of the RF pulses. Jeez, that's terrible. Terrible writing. Alright, so we get oscillation in KY for EPI, or KF for opposed null pulses. That gives us a field of view over 2 side lobe in each case, because we've got this oscillation across the phase encoded direction in K-space. And so then that gives us this huge side lobe, and it's really catastrophic to the performance of the pulse. All right, so that's it for these different effects of different practical effects that we get inside the scanner of echoplanar and spectral spatial pulses. And so next time, now we've covered everything that we're going to cover in spiral pulse design, and EPI and spectral spatial pulse design. So that's everything we're going to talk about for small tip angle RF pulse design. And so next time what we're going to do is finish this up then with talking about iterative RF pulse design, and then we'll move into designing large tip angle slice selective RF pulses using the Chenard-Leroux algorithm. All right, thanks.